some observations about sorting on modern hardware. Let's first do some general observations about the kinds of sorting algorithms that you would use in a standard library specifically, is what we're talking about here. And then you can see that comparison-based algorithms are common in practice. It's a very general model, so that's appropriate for standard libraries. And as you will remember from any kind of data structures course that you've had, there is a lower bound of log of n factorial comparisons, which is approximately n log n. So this is not even big O's. This is actually almost the same, even if you take the constant factors. Next observation, quicksort and merge sort are actually pretty good sorting algorithms in practice. Maybe you do intrasort instead of quicksort, but certainly in expectation, they work pretty well on real hardware. They have decent memory locality, and they are close to optimal as it regards the number of comparisons. There are also algorithms that are not comparison-based, so you get, for example, counting sort or radix sort for integers, which might sound like they are very good in practice. You could save a log factor there, and depending on a lot of context, they could be good. But claims of general, extremely good practical performance are disputed. There are very recent papers that claim, like, well, actually, it's not that good. You can pick your inputs to make it look good, but for a general purpose sorting function in a standard library, this is not really what you want to be doing. So for the rest of this talk, we'll also restrict ourselves to comparison-based algorithms. But still, let's think about sorting integers for a second, because, well, a lot of the time what you're doing is you're sorting integers. So comparing two integers should be vanishingly cheap in comparison to memory access, because comparing two integers is basically subtraction and then seeing if it's positive or not. So that's really just this one step on any reasonable processor. So if the comparison itself is so cheap, why would we evaluate an algorithm by how many comparisons it actually does? And so what they do is they look at a Pentium 4, which was a recent processor at the time, which for that time has a high bandwidth and a long pipeline. And so experimentally they see that their quicksort implementation has runtime C times n log n, with constancy throughout the memory hierarchy. I mean, what you might expect if you're memory bound is that once you run out of different levels of caches, then you might expect C to go up, but it doesn't for them. So is their quicksort code doing comparisons all the time? Is that what the processor is busy doing? And their answer for them is they say no, because they look at the runtime, they divide it by n log n, 8 nanoseconds, which is, if you do the calculation, potentially 72 instructions. But, well, what are the other 71 instructions doing, or as the case may be, not doing? To understand that, we have to talk about processor architecture a little bit. And the first thing I want to talk about is dependencies, and in particular, two kinds of dependencies. And the first is a data dependency, which is if an instruction needs the result of a previous instruction. So for example, if I have two numbers that I add, and then the next instruction says double that register, well then I need the sum before I can double it. If you have two instructions, the first calculates an address, and then the second says read from memory from that address, then certainly you need to know the address before you can go read there. Instructions that have a data dependency between them need to be some number of pipeline stages apart, depending on what these instructions are. So you might have to briefly stall the pipeline for this to work out, but this is generally not a real disaster. The other thing that has the potential to be a disaster is a control dependency. So you get that from conditional control flow, from uncertainty about which instruction is next. And this uncertainty is terrible for a pipeline processor, because you must either wait for this information to be available and then no instructions are coming into the pipeline, so this wastes a lot of time. Or then what you get in modern processors is a branch predictor and speculative execution, where you're like, oh, well, let's do it. And then if it turns out that we were wrong, we throw it away. And what this basically does is a misprediction must flush the pipeline. And so depending on how deep your pipeline is, and pipelines are deep nowadays, 31 and a Pentium 4 is what they say in the paper, you get this humongous penalty for a misprediction. And this penalty is proportional to how deep your pipeline is and the misprediction rate, because it's basically an expected value of having to do this. And this is very relevant for comparison-based sorts, because as we just mentioned, there is this n log n lower bound for comparison sorts, and this information theoretically means that if you only do about n log n comparisons, they must be about 50-50 yes and no. Otherwise, you're not getting enough information from them to do sorting. So basically what this line of argument tells us, actually yes, performance on a modern processor is linked pretty directly to the number of comparisons, because the thing that's expensive is a pipeline flush, and a pipeline flush happens on a mispredict, and mispredictions must happen about half of the time. So this is a bad state to be in. Is there something smart that we could do? And certainly our algorithm is going to have to depend on the comparisons, otherwise we're not doing anything. But the idea that you might have is, well, it's the control dependencies that are bad. The data dependencies aren't that bad. So could it be possible to organize our code in such a way that the comparisons that we're doing are a data dependency instead of a control dependency? Maybe that's a little bit hard to imagine. But let's get to the second thing about processor architecture that I want to talk to you about, which are predicated instructions. So this is the idea that you make your processor in such a way that it is possible to mark an instruction with a condition. And what that means in this pipelined processor is you always go do the instruction, you decode it, you do whatever you need to do to this instruction to be executing it. But then in the end, maybe the actual execution, or maybe even just a write back, you only do if the condition was true. So that is a kind of instruction that says increment register A, but only if the last comparison was true. And the crucial thing here is that this does not bother the pipeline. We're always doing this instruction. There is a data dependency from the last comparison to this instruction, but not a control dependency. We're always doing this instruction, but maybe we're throwing away the result. And if this sounds like a weird thing to do, interestingly, this is already how conditional jumps work on common architectures. So on Intel, the conditional jump, the way that you do a branch, the way that you compile an if statement, is not an instruction that says jump to this label if A and B are equal. That is not an instruction that you get. The way that it works is two instructions. First, you have an instruction compare A and B, and then you have the next instruction that says jump to this label if it was equal. This is a predicated jump instruction. And of course, there is a data dependency now between the compare instruction and the jump instruction. And then because jump instructions influence the control flow, then this becomes a control dependency because you do the jump or you do not do the jump. But basically, this is a predicated instruction. Some processor architectures have a very general predication. There was the Itanium architecture, which is a fun thing to look up if you care about processor architectures, but it wasn't successful in the market and it was fairly quickly discontinued. In mainstream architectures nowadays, you tend to have a conditional jump. You tend to have some instruction that reads a status flag into a general purpose register as 0 or 1, and then you can have a normal add instruction, and together this is kind of a predicated increment. Or you could multiply by this, and then the result either becomes 0 or it stays what it was. You can play tricks with that. And another one that's pretty common is the so-called conditional move, which is an instruction that basically does, if particular condition, then X gets Y. Or it's more of the Intel version. ARM has the conditional select, which is X gets, depending on condition, either Y or Z. Maybe not literally predication, but it allows you to do similar tricks. Okay, so this is a thing that mainstream processors can do. How do you make it do these things from a high-level programming language? Because this is not really anything that mainstream programming languages are well set up to express. You have if statements, but you don't really have control over how they get implemented. You can't really say, I want you to do this conditionally, but not have any control dependency. However, As you may not know if you never look at the disassembly of what your compiler does, compilers are actually pretty good at using these predicated instructions. It's just not necessarily reliable. So if you're doing something and it's really important to you that these predicated instructions get used and that there are no control dependencies, then unfortunately you really kind of have to look at the disassembly to see that the compiler understood what you were trying to say. So first of all, let's do a very simple condition and compile it without optimizations turned on. So I have this function, it takes a bool, and if it's true, then I return 1, else I return 2. So let's compile it without optimizations, and then what I get is the following code, some stuff that I've omitted because it doesn't really matter for what we're talking about. And then what we're doing is first we compare this boolean, we got it in this D register, we compare it to 0. If it was equal, so that's false, then we need to go to the else, and then we jump to the else, and then we prepare to return 2 because we put 2 in the A register, and that's how that works. And then we fall through, and then we return it. If it was not equal to 0, then we don't take the jump, and then we end up here. We prepare to return 1, and then we jump to done, and then we're here, and then we actually return. So this has a control dependency specifically on this jump if equal instruction, and this is how you might imagine that the compiler or your processor actually does this if statement. Now let's see what happens if we turn on compiler optimizations. Exactly same code, and now what it does is you can already see it's a much shorter program in this way. What is it going to do next? It subtracts b because this boolean b is either a 0 or a 1. So then if it's true, then we want to return 1. So it's just, you could write the C++ code return 2 minus b, which compiles and gives the same result. So this is actually something that the compiler does. If you turned on optimizations, and this is the literal disassembly that I got. This is a little bit cheeky, but there's no control dependency. This is straight line code. It's just 3 instructions, and it does the thing. One thing that you can note here is that you get insane bugs if you ever call this with anything other than 0 or 1. You're not supposed to call it with anything other than 0 but 1. But if you look at this code, you might reasonably expect that certainly it cannot return anything other than 1 or 2. But if you unfortunately pass it uninitialized memory or something, then your compiler put you in a position where you're going to be confused. Right? I wanted to show you how conditional moves get used, and then I wrote this code and I disassembled it, and I found this cheeky bit of code. So let's actually put different constants. So return 42 and 1337. I get the code that I expected the first time. So what does this do? First, we set the status flags from our parameter, set aside 42 in register C. Then we're going to prepare to return this constant in A, and then we're going to do a conditional move if not equal, putting the 42 in the return register. So if B was not 0, we're going to overwrite the 42. Now you might notice here that this test instruction is way up here, and the conditional move is down here. The moves are in between, and they don't need to be. These moves could have been above the test. I'm not entirely sure why the compiler chose to do it in this order, but I might conjecture that this might help with the data dependency between test and the conditional move, but I don't know all of the details about this, so that may not be why it did that. But in particular, I want to repeat, compilers are pretty good at implementing conditional execution using predicated execution, but you have to check if it's important to you, because it's not a language feature. You can't really tell your compiler you have to do this. In general, it's not a bad idea that you trust your compiler to do it if it's a good idea. But if you're doing computational experiments and you really want to see what this does and how that works, or if you think you know better than your compiler, then you really do have to check.